marked the wrong ones in my book. Hang on. It was what? It was just 2 and 3, right? What it was? Alright, 2 and 3. Why can't a given mass of steam at 100 degrees Celsius burn your skin more severely than the same amount of liquid water at 100 degrees Celsius? I already said Chris could have it. Alright, Chris.
I said the steam will not burn as bad because of evaporation.
Alright, so it's saying that, okay, if you have steam and you have 100 degrees Celsius and you have the same amount of steam and water, they both hit you at the same time. Which one will hurt worse?
The water, because the water would sound like
You sure?
yes.
Okay, what's gonna happen if you have steam touch your body? What's it gonna do?
Condensation
Okay, so it'll be losing heat. So where's that heat gonna go if it's touched you?
into your body.
Into your body. That's how come if you've ever gotten a steam burn, it hurts. How many of you have gotten a steam burn before? That's the reason why you think, okay, there's not that much of it there, but why is it not so bad? That's the reason why. It's because steam, remember, of the 3 states of matter, solid, liquid, and gas has the most energy just being in that state. So even though they're at the same temperature, it has more energy on the inside. So if it touches you, it'll condense or put all that energy into your arm. Okay. Other 3 common states of matter. Common states. So that's what it's talking about for that one. So steam. That's the reason why if you ever gotten a steam burn, even though it seems like that's not a lot there, but you realize, oh, it hurt really bad, or it might hurt your face depending on what you did for it in order to get the steam burn.
That was my face.
You did it on your face?
Yeah, I was even over the stove.
Ethan, I'm sorry.
I was in the bathroom like 3 hours after that.
My mom, she asked me to
the food you
pour
ate or what?
noodles. Like, you know how you're supposed to like drain noodles in like the colander?
Oh yeah, that's
She
what
didn't
that was
tell
what
me
it was.
that you're supposed to always pour it away from you, not towards you. Like, I just didn't, I wasn't old enough to think through that and to realize that. I just didn't think about it. So whenever I poured it, I had my arm like over the side of the pot where all the steam went up and hit my arm. I had this nice little crescent-shaped burn mark on my arm for about a week, and I went to my mom, look at it! You didn't tell me, look at it! You're old enough to know better, use your head. Go get some ice. Okay. And so that was basically my day. Number 3, what is the difference between heat of vaporization and heat of condensation? Alright, Brendan.
Heat of vaporization goes from a state of liquid to a state of gas. While heat of condensation goes from gas to liquid.
Yeah, so basically it's the same amount, but it's the idea of, okay, what state are you going into? We'll talk more about it once we get to that section. Alright, number 4. You have to sit quiet while I check other people's work for it, because we went through months of it yesterday. Alright, so propane. This is a major component of LP gas is used in heating homes and cooking fuel. So it's also in RVs and camping equipment. When propane is burned, reactive oxygen, CO2 and H2O are produced. Alright, Quentin. Jimmy, as a side note, Ethan and Chris asked me in study hall to come up asking certain people for help now. So, Quentin, did you figure out what the balancing equation was for this first one? Because that's what you have to figure out first, right, the balancing equation. I know Ethan and Chris both got it. That's how come I'm not calling on them, because I know they got the right one.
Negative 1 to 3.8.
What's the balanced equation?
No, that's wrong. C3H8.
Yep.
And then CO2. No.
It's reacting with oxygen or burning with oxygen. So it's O2.
What's O2? Arrow.
Yay!
CO2 plus H12.
Okay, that's the basic equation. Now you have to balance it.
Okay, put a 3 in front of the second one. And then put a 2 in front of the other one.
Right, this one? Why? Because I have 3 carbons here and I have 3 carbons here. Unless you really
Oh, that's
want
right. I
to.
was looking at the 2
Okay.
under the other one. And then put a 4 on the 8 on the other side. And then put a 2 right there. Yeah.
That's it? Close. Alright, so your carbons are balanced, your hydrogens are balanced. How many oxygens do you have right here?
4.
How many oxygens do I have over there? Okay, I have
Oh.
2 here, so this is 6
So,
plus
yeah,
4.
I see the other 2.
It's okay.
So put a 5 right
And that'll give you how many?
there.
Yay, is it balanced now? Yay! So, good job figuring it out on your own. So, if you worked it out just now, or if you already figured it out yesterday, good job figuring it out. Alright, number B, well, part A still, we had to figure out, okay, what is the total heat or the total enthalpy of formation that changed for this reaction. Alright, so, I know you got the right answer, so stay quiet. So, Ethan, I don't remember if we worked all the way through this
Nope.
for you. Alright, Ethan, what did you get for your answer? This one, so Jamie can see my work.
Negative 2045 as the enthalpy change or whatever. Is that right?
2044 or 2045?
45.
Is it?
Based on that's right.
You were very close. You must have rounded off somewhere to get it slightly different.
Is there a
somehow.
.8 in there?
What?
Is there a .8 in there somewhere?
Yep.
So 2044.8?
Oh, no, not like that. I thought you meant like, is there just like a 0.8 anywhere in the values for it? Alright, using the table on page, I believe it's 84 for it, to figure out, okay, what is the standard heat of formation for substance? You asked me this a whole bunch of questions in study hall, Chris. You have patience and you
You did not help me, I got this all by myself,
Oh,
10%,
you
100.
guys
Oh,
know
yeah,
every
100
step,
quiet. No,
every step, Chris,
listen.
every single step.
I'm
Where's the
giddy.
proof?
I remember, and they can vouch for me over how many times you asked me questions. Do you need
Hey,
classwork?
what is
You're
this?
gonna sit there
What is
before-
this?
Do you need classwork? Sounds like you need classwork. Then sit quiet and be patient, cause I helped you a whole bunch in class, I helped you a whole bunch in study hall, so you're gonna sit there and be quiet, I know, but no. They're trying to figure it out, so just wait. Alright, so what is the heat, standard heat of formation for the carbon dioxide? What do you have for that one?
103.8.
Alright, 100.
Or carbon dioxide?
Carbon dioxide. Just gonna draw arrows.
393.5.
Positive or negative?
300, I'm about to say. Negative.
Good job. Alright, what about H2O?
241.9.
Is positive or negative?
Negative.
Good job. Alright, what about for
So
the
3 and a 4 before this, right?
We will in a second. I'm just figuring out I'm just the values up right now. What is this one?
Negative 103.8.
Good job. Alright, and then what about this one?
Nothing.
Why?
Because it's oxygen.
It's free and uncombined, but yes, you're right. You don't care about it
No
because
one
it's free and
likes
uncombined.
oxygen.
Alright, so this one has an understood 1 in front of it because I have 1 molecule. How many carbon dioxides do I have?
3.
3. How many waters? 4. Should have left more room. So it's 3 times this plus 4 times this. That will give you your total amount of enthalpy change for the entire product side, which is what? I'm glad you calculated it. Proud of you. Alright, couple seconds, otherwise I gotta go check Ethan's. So, 3 times this.
Negative 3,114.9.
Okay, I'm not quite
Oh,
sure how you.
well, I just added.
Alright, so it's 3 times this, and then you add it to 4 times this.
Nice.
Got a little plus sign there. Couple seconds, otherwise I gotta go. Alright, Ethan, what'd you get?
No, negative
2,148.6.
You're close, what'd you get?
Negative 2,147.7.
There you go. So, you must have missed off a decimal point somehow, Ethan, so you got close though. So, remember, this is just the product side. So, how do I solve now? What do I do if I figure out, okay, well this is the total change for the reactant side then. Which one? So, do I subtract this one from this one or this one from this one?
That one to that one.
Okay, so
That
products
one,
from
that one.
reactants or reactants from products?
That one to that one. Reactants to products.
Yes, that, okay, it's the idea that it's the products subtract the reactant. So this number is on top if you're setting it like a fraction. So, it would be like this. Now, whenever you do a subtraction of a negative, it turns into the addition of the positive. So, what is the final answer? Chris, I'll let you get the final answer for this one.
2,318 kilojoules.
No.
2,318 kilojoules.
That's not the, say it one more time.
2318 kilojoules.
That's not the answer you gave yesterday.
Per B.
No, we're not that B yet. So, first go for part A.
I got negative 2,044 kilojoules.
Good job. Now you're right. Your calculator will say something like 2,043.9. So you round up for for 4 sig figs. And what's your units?
so close.
You were close, you just would have had to
I
miss
was
another
one number
point.
away.
Alright, so, your book says, okay, what if you have 50 grams then instead? So if I have 50 grams of propane, how do I go from grams to mole? This is how much heat is generated from 1 mole. What do I do?
Divide
By?
2044.
Nope, because this is how much heat is given off by 1 mole. How do I go from grams to mole? What do I use?
Multiply. Oh yeah, you do all of that. So you do it. Okay, hold on, just 44.094.
So that is propane, what did you say it was?
44.094.
Yeah, put 0.094, whoops. So what do I do now?
I got a bigger number than that.
You divide.
It should be C3H8.
You divide. Like.
Alright, so
Oh, I got 44.094.
That's all right.
That looks like 8.
Alright, so 50 divided by 44.094. Okay, what do you get? Alright, Chris, let's give the answer to this one. How many moles?
1.1339.
1.13 what?
39.
Yeah, your book just rounds them just to 4 sig figs, just to be done with it at that point. This one goes, okay, that works for it. So this is the number of moles. Now what do you do?
You do it by
Nothing.
2003 times it to the negative 3,300.
Negative 3? You times
Negative
it by?
2,000.
Oh, okay. So you multiply this number times this number?
Correct.
Yes, now what do you do? Now what's the answer for that one?
I got negative 2,318 kilojoules. I got positive, but I think it's supposed to be negative.
Yes, it is supposed to be negative 4. Now, this one is super close for it, because how many, I made it super messy.
Point.
Apparently. So, this one has 3 sig figs starting off with, so how many should it have?
Should be negative 232.
Or 200.
Or negative 2,320.
Should it have a decimal point?
Yes. Yes.
Yeah, it does. So the secret of what? Yeah.
So, do you want 4 sig figs or 3 sig figs?
Three.
So, should it be a decimal point? No, you shouldn't. Don't listen to Ethan. So, how many, so what's the units for this then? If this is kilojoules, then this should be
Kilojoule.
This is also kilojoules.
Kilojoule.
Alright, so that's the answer for both parts. Alright, anyone have any questions about how to solve either one of
Never do
those?
this again.
I mean, for your test next week, yeah, but
Are we
for,
gonna only test next week?
what?
Are we gonna only test next week?
We're gonna talk about history after today.
No, I mean like for every other class. Do you know?
I think they're all supposed to be happening next week. I just got to mine early and I did early. But yeah, I think everyone's supposed to be having them. It depends on where it falls, but next week's the 3-week mark.
This is gonna be fun.
I'm gonna go kamikaze to the World Trade Center.
No, alright.
That was bad. That was my bad.
I would
It's just, I
say-
didn't have a filter on that one. That was
No,
my bad.
do
That
not
was
joke
serious.
like
That was
that.
seriously my bad.
Yeah, don't do that again. Alright, we're going to play the dice game. They don't have a whole lot of terms yet. There's just mainly math in this section. That's the reason why I would say, okay, if math is your thing,
So it's not
learn
many
how to
cards,
solve
many
it.
darts? So
By
it'll
the
be
time
quick
it
if there's
takes-
not many.
Are you gonna be quick with it?
Yeah.
They're gonna be very fast.
Nice.
Okay, we can play darts as long as y'all move quickly for it. And get your German.
Or not I.
Okay, try not to get too loud around Jimmy, because Jimmy can pick up the darts much better, and I can't.
Seriously?
She can hear it really well, because I went and watched some of the videos again. Quentin probably noticed too as well how loud
Is
y'all
it actually?
are.
I didn't think it was that loud.
I know
It
Quentin's
picks it
loud.
up
When I was
extremely
watching,
well.
Quick,
but
very
then
loud.
again, I didn't watch it when there was actual people there.
Yeah, no, whenever it's just me, it didn't pick up me very well because y'all are so close to it, it picks up y'all extremely well. Alright, so be sure to remind me to take Jamie off the ceiling in a minute, so that way she doesn't have to stare at the ceiling for the whole period. Alright, we'll start with,
Oh, she can hear me.
alright, Chris, so thinking back over it, what is the symbol for enthalpy?
Delta. No.
Is that the final answer?
Yeah, Delta's final answer.
Nope! Let's go backwards this way.
Oh,
Enthalpy.
uh,
Alright?
H.
H, write it down. H is for enthalpy.
so only 2 throws or something?
You may get 2 throws. Germans though.
Y'all remember why?
You mean Superman?
Alright, hurry, can't take too long.
Sorry, my hands are red.
Yeah. Don't ruin on my darts.
Used to red darts, my best friends.
This is why my darts are
19.
long. This is why I've only had these for less than a year.
Use red dart.
That's what
Break's
I did.
first one.
Alright, what is a device that's used for measuring heat flow?
We just did the sixth grade. It's like similar to like, it sounds like a food or something, right?
Oh, you're thinking of the food unit.
Is it like calorimeter? Something? It's like
Okay, I'll take it directly. So, calorimeter, it looks like calorie
What a
meter, but
guess.
calorimeter.
yeah, it's a food calorie.
Okay, calorie is technically a food unit, it's not necessarily a food unit. Or even just calories means you're eating like raw sugar.
Anyways. Okay. Cody.
It's not my dark stuff.
Mama,
Alright, Quentin, what is the symbol that means change?
Delta.
Delta.
We keep nailing this, hardly red dart's about to be the good ones.
Better go quick one.
She can't see you. She's there.
Why?
We just have to remember, because there was one day she had to awkwardly watch the ceiling for like 20 minutes. Hey!
I thought
Alright.
it was on slide and whip it.
Alright, what is the combination of symbols that stands for standard enthalpy of formation?
Let's start with
It's a combination of symbols, so like what do we use
Oh.
to represent that?
Delta H.
Delta H,
F degree.
with what?
Degree H.
Yep, good job. That's the degree symbol that has a little subscript F.
Not a guess. How would I guess that?
Here's the board.
You'd have to know.
Well, there goes those cards. Four darts.
Poor Moses.
Alright,
That's not Moses, that Christopher.
Whoever threw that dart.
alright, let's see, at the standard state, what is an assigned enthalpy for a free and uncombined element?
Zero.
Zero, understood, zero, with a reference point.
I would do it. So I can make 100. You see why we're using the blue darts? Because it's supposed to be easy.
Alright, what is the substance required to cause a unit rise in temperature of a unit mass of a substance?
What?
What?
If I want to raise like 1 gram of water 1 degree, like what do we call that? It's the amount of heat required to raise a unit mass of a substance by a temperature degree.
What is Star Wars?
It is S, but it's Quentin's turn.
It's still going to get
Oh, no.
right.
Yeah, he is.
Okay.
Is there 2 words?
Yes,
Specific.
Oh.
Heat?
specific heat.
I forgot second word for a second.
Amount of heat required to cause a unit rise in temperature by a unit mass of a
That's
substance.
18.
Hey, alright, that's pretty much all of the recent stuff because
So I
we were
win.
doing math. I think you probably did. Alright, Ethan, how many points did you get?
Yeah, he probably won.
It sounds like you probably won.
24.
Yeah.
Alright, Ethan won. So, it's your study this section. Not too loud, keep it reading. Now, that's one reason as to how come you want to, oh, I'm sorry. Just jumped over my screen, sorry, Jamie. So that's part of the reason why though whether you want to be studying with your equations, because this chapter is predominantly math. So there's not a lot of terms. So if you're banking on, oh, there's gonna be terms in the test. I didn't really think of it. That, yeah, there's some, but there's way more math. So if you're struggling with math or if math's not your thing, make sure you're paying attention to get extra help. So that way you will be able to do well on this test. This test in particular is very math heavy. Alright, we're talking about heat and changes of state. Alright, think about the 3 common states of matter. Which one has the most energy? Chris. Alright, which one has the least? Solid. So, this is one reason why we're talking about yesterday with the idea of going from one state to another. Now, if I'm going from a solid to a liquid, do I have to put heat in or do I have to take heat out? Ethan. We're going from a solid to a liquid.
Put heat in.
I have to put heat into it. What if I want to go from a liquid to a solid? I have to put heat in or take heat out? You have to think these through. Take heat out. So that's the idea of this. So that's the idea of having.
I think that's quite literally the opposite of the question you asked me.
Yeah.
Quite literally.
But it's the idea of, okay, it just depends on what direction you're going. If you're putting heat into it, that is heat of fusion. Now, anyone remember what the technical term is for taking heat out to go from a liquid to a solid? We use it heat of fusion for both directions for like convenience sake, but your book tells you. Does anyone know what the other one is?
Is it fusion?
It's heat of fusion. With the idea of fusion has to do with the idea of melting.
Yeah, what is the other term, sorry?
C.
C?
Anyone know? Alright, heat of crystallization. So,
Oh, I
it's
thought
the
you were
idea.
asking about something we learned a while ago.
Oh,
It's like-
no. It's just the idea of, okay, technically, if you're going from a solid to a liquid, that's heat of fusion, you're putting it in. Technically, if you're taking it out, going from a liquid to a solid, that's heat of crystallization. But it's the same amount. Like for water, and I use water as an example, you put 334 joules in, you gotta take out 334 joules. So, since it's the exact same number, you're just putting it in or taking it out. Your book just uses heat of fusion, and scientists will also use heat of fusion instead of getting technical and using two different terms. They just say heat of fusion, and it's understood that, okay, if it's negative, then you're just taking out that one. So that's just what your book's talking about. Alright, the next major one is heat of vaporization on page 86. Alright, heat of vaporization, my steam did not show up well on the slide, so I'm sorry. There's supposed to be steam up here. It just looks really pale, like a very light blue, or you can't see it at all. So, you'll notice that this one has way more amount of heat to it than it did in the first one. With the first one, with the idea of if this one only took 334 joules, this one takes 2,260. Why do you think it takes so much more energy to go from a liquid to a gas?
Because it takes more energy.
Why?
Because
Because it's
the
harder.
law says that.
Yes, but I mean like why?
Because God says that.
Okay, think of it. No, think of it. What do we call? Okay, this is not related to chemistry, but like right now. But what do we call it whenever you have the attraction of a substance to itself? Anyone remember? This is way back there.
Magnetization.
Not
I'm about to
magnetization.
say that.
It's way back there. Starts with C.
Condensation.
Nope. Alright, cohesion. So if you remember way back physical
Really
science,
think I'll remember that word?
cohesion is the idea of, okay, it's attracted to itself. Adhesion means it's attracted to something else. So cohesion, water has really strong cohesion where water likes to be next to itself. So if you wanted to go from a liquid to a gas, is the water molecules, are they still next to each other? Quentin? No. Now, if you're going from a solid to a liquid, the water molecules are still next to each other. They're just not locked in. Like in a solid, they're locked into it, basically frozen. But if you melt them, they're still next to each other. So you're basically just giving them energy so that they can move or flow. If you're going from a liquid to a gas now, you gotta give them enough energy to basically have them get enough energy to overcome atmospheric pressure, because they're turning into a gas, and to also separate from each other. That's how come this one has so much more energy associated with it. Alright, so if I'm looking at my water and I'm putting my heat into it, is that positive or negative? Positive. So I go from 100 degrees Celsius to 100 degrees steam. What if I want to what if I want it to go back to being a liquid? What do I gotta do? Take out heat. So for this one, again, it's the same amount. It's just the idea of, okay, you either putting it in or you're taking it out. Yes, Ethan.
Freeze it.
Nah.
It goes back to it.
If you're going back from a gas to a liquid.
Alright, just freeze it.
Yes, what do we call it? It says on the slide. It says, Ethan, condensation or condense. So with the idea of it's going backwards. So the idea of, okay, you put it into it, that is a positive value, taking it out, it's a negative value for it. Your book points out, technically, it's heat of vaporization. Vaporizing is another term for evaporation. So that's how come your book's given it to you as heat of vaporization. And then also technically, it's heat of condensation if you're taking it out. But again, scientists and your book knows, okay, it's the same amount, it's just the idea of putting it in or taking it out. So they just use heat of vaporization. Alright, anyone have any questions about that idea or that concept? Alright, so let's say though that, let's say I want to take water and I don't have just 1 gram of it, I have, we'll say 50 grams. So I have 50 grams of water, and I want to go from 50 grams of water to 50 grams of steam. What do I have to do? What, Ethan? You looked like you said something.
Put heat in.
That's not even-
You take heat out.
If I want to go from a liquid to a gas?
I never said that. I said you put heat in.
Alright, you put heat into it. Now, how much heat, according to that slide, your book shows this as well, but according to that slide, how much heat do I have to put in if I want 1 gram to go from liquid to gas?
2,260 joules.
Yeah, but I don't have 1 gram, I have 50 grams. So what do I have to do? Figure this out.
Divide by 50.
So 50 times this would be what? I did not work this out ahead of time. So 2,060 times 50.
It's 113
I was
calories.
doing my head.
It's 113
It is
calories.
150,000. So 130,000. So that's basically what the equation at the top of page 187, not 187, sorry, 87 is giving you. So look over at top page 87. This is your next set of equations that you need to know. That it says, okay, the heat of vaporization, because remember what does Q stand for, Quentin? Chris, what's Q stand for?
What?
What's Q stand for?
Did we say that at the
In
same time?
science, what does Q stand for in thermodynamics?
I know it.
Okay, everybody next.
Uh-huh.
Alright, Ethan.
Heat.
Heat. So whenever it says Q vape, it means with the idea of Q is the heat of vaporization. Doesn't mean like vapor. So that's what it's talking about with Q with vape. Is it means the heat of vaporization. So for this one, you just take the mass times the delta H for that change, how much heat is required to cause it to evaporate. So that's basically what we just talked through. That if you know, okay, what is the delta H of vaporization or the change of enthalpy or change of heat for vaporization, you just multiply that by how many grams you have. Figure out, okay, am I going from a liquid to a gas? If I'm going from a liquid to a gas, should my number be positive or negative? Chris? Positive. What if I'm going from a gas to a liquid? Negative. So this is the only equation for this one. You just have to know for vaporization, just know, okay, where am I going? If it's going from one state to a higher state, it's positive. And then the other direction, it's negative. So you just multiply the mass just literally by that amount. Your book lists off several different the delta H's of fusion and vaporization and their melting points at the top of page 87. Be sure to read, pay attention, what are we actually looking for, because they give you a bunch of information in that section. Alright, to find it for fusion, it's the same basic equation, but they're just saying, okay, for fusion, it has a different amount. So like how we looked at with water, that this one is 334. So if I wanted to go from a water to ice, what would I have to do if I have 50 grams and I want to go from water to ice? What do I do? I'm not responding ahead of time either. Alright.
Take it out.
What?
Take it out.
Take it out. How much heat if I want to go from 50 grams of water to ice? How much is that?
330.
Put the pressure.
Okay, not quite,
Or,
because it's 50 grams times 334.
Put the pressure.
16,700.
Not quite. So it's
I was trying to read it off this
16,700.
calculator.
Cheater. So 16,700. Alright, if I'm taking heat out, is that positive or negative?
Negative.
Negative. So that's the only thing you have to watch out for. Alright, so your book gives you a phenomenal, helpful practice problem on page 87, because your book starts to combine all the ideas of doing the idea of specific heat and heat changes, and then raising temperatures, and then going from one state to another. This problem looks super complicated, but it's not. It's basically 5 problems smashed into one giant problem to help you get practice for it.
Wow.
Alright, so let's go through it though, because this problem is actually amazing for help trying to get you ready for your test. Alright, so going through it, let's say it says you have 25.0 grams of ice. And and it starts up at negative 50 degrees Celsius. Negative 50 degrees Celsius. And I want to change it to steam at 110 degrees Celsius. Alright, so if I'm going from ice to steam, how many state changes is that? 2, because I gotta go from ice to liquid and then from liquid to gas. So I have 2 state changes. And then also I'm going from 50 degrees Celsius to 0 degrees Celsius, and then I have to go from 0 to 100 degrees Celsius with water, and then I have to go from 100 degrees of steam to 110 degrees. So basically it's 5 problems all at once. This one is a great practice one. Alright, so let's go through it and let's figure this out. So, your book points out you're going to have to use this table on top page 87, but then you're also going to have to use it, the specific heats of ice and water and steam as well. The specific heats are on page 81. Now, you might remember what specific heat of water is because we use it so much, but you don't have to. You'll be given both if you need it for it. Alright, so let's go ahead and let's do the temperature changes first, and that's the easier, at least I think that's the easier one for it. What equation do we use if we're using specific heat, mass, and temperature change? What's that equation? Ethan?
Say it.
If you're using specific heat, temperature change, and a mass, what equation do I use?
C equals Q over M delta T.
Good job. Except, I know what the specific heat is, I'm finding Q, so how do I reshift this around to get this into a problem I can actually use it to find heat?
No, we're using what?
We're using specific heat, we're finding Q.
So C M delta T equals Q.
Yep, so basically I take this, I'm gonna move it over here so I don't forget. So Q equals Cm delta T. So this is the version we're gonna be using to figure out with the heat changes, because we're going from one temperature to another. Alright, so I have to go from negative degrees Celsius to 0 degrees Celsius. I have to raise it to that temperature, because that's whenever ice changes from ice to liquid water. So, what is that degree changes? What's the difference between 15 degrees Celsius and 0 degrees Celsius? 15. So that's my first temperature change. So 15 is okay. Is it going up or going down? That tells me it's going up. So it'll be positive or negative? Positive. Alright, how much mass am I starting off with?
25.
25. I'm gonna write 25.0 so I won't forget my six things. Alright, and then what specific heat of ice? You're gonna have to look this one up. So it's on page I think 81.
2.06.
2.06. So 2.06, I'm gonna leave off the units for it. Alright, so what is this first amount of heat that is required just to change it by this amount? Alright, close your books since y'all are cheating and looking in the books for the answer. So y'all get your books unless you're looking it up.
I'm watching.
Nope, close them. Alright, type it in the calculator.
One time.
Say it one more time. Good job. So it should be positive or negative? Positive, because you're going up. Alright, 7.725. We're not gonna worry about sig figs right now, we're just gonna write them off of this. This is in joules. This is step one, just from going from ice just to melting at that point. So, we're gonna go ahead and do the next temperature conversion, because I don't wanna get stuck halfway through it. So, let's do the second temperature conversion. So, I have to go from liquid water to water's boiling point. So, what is the boiling point of water in Celsius? Anyone remember? You say 212?
100.
That's Fahrenheit. 100 degrees. So if I'm going from 0 degrees Celsius to 100 degrees Celsius, what's that temperature difference? Ethan.
20. Wait, say it again.
If you're going from 0 degrees Celsius to 100 degrees Celsius.
100.
100. Alright, 100 temperature difference. Alright, what mass am I working with? What mass? Like what amount of water am I working with?
2.1.
Good job. 25. Alright, and then what specific heat of water? Anyone remember? If not, I'll just tell you.
3.8.
Whoa. 4.18. But again, you don't have to memorize it, but you probably will. Alright, type this in. What do you get?
10,450.
Say it again.
Give me some.
10,450.
Good job.
I was in my head.
We'll just write it down here. So 10,450, still joules. So again, that's for part 2 with the idea of heat changes. Alright, so we're not stopping at just 100 degrees Celsius, we're going to 110 degrees Celsius. So what's that temperature change? I'm gonna leave the 25 seconds because that doesn't change.
110.
Alright, I'm going from 100, yep, so 10. Alright, so the specific heat of steam, I'll tell you this one as well, is 2.8. Alright,
I was
so,
gonna say that.
what?
I was gonna say that.
Oh,
I'm just kidding.
700.
Alright, 25 times 2.08 times 10.
520.
There you go, 520. So, 520 joules.
520.
Alright, so that's our temperature conversion. So, that was what our first problem was.
It's the
Now, the
reactor.
second part, we have to go through the state changes to say, okay, I have to go from a liquid to a gas and from a solid to a liquid. Alright, so so the heat of fusion for water, I'll go ahead and tell you this one for it, is 334 joules. So if this is the heat of fusion for 1 gram, what do I do?
Multiply it times 25.
Good job. So 25 times
I was gonna
what?
guess that. 8,350.
Good job. 8,350 joules. Alright, and then the heat of vaporization for water is 2,250 2,260. So 25 times 2,260.
56,000.
64,000.
Ooh, 56. 56,000, what was the rest of it?
500.
Good job.
You're a lot.
Alright, last step, because the equation asks how much heat is necessary to convert everything to go from that negative 50 degrees Celsius to 110 degrees Celsius. So, now that I know all 5 parts and it asks for what's the total heat, what should I do?
Add 'em all.
Add them all up. So, that's the reason why I wrote them off to the side, so you'd be able to see them all. But yeah, you add them all up together.
Okay, what we're doing now.
76,592.
I should have talked about it.
Say it one more time, so,
76,592.5.
75,000.
76,500, no, or 76,542.5.
Alright, I think you got off slightly somewhere, because that's what you said, right? Alright, double check it really quick, because it's 772.5 plus 10,450 plus 520 plus 8,350 plus 56,500. So you have
You're
the,
100% sure that answer right there is right?
This was.
for this one?
Yeah.
There, one more time, because you're slightly off. Like you're off by
I
like
see
one.
why it was, yeah, I forgot to add the 50 somewhere, I see why I was wrong.
So just add 50 to it.
Yeah,
If this was
Wait,
40,
92,
just
yeah.
add 50 to it.
9, 2.
There you go.
But that's what I said.
I heard 4-2.
No, that's what I said.
Alright, make sure that you're saying it clear though, because I heard 4-2 for it.
He said, Ethan said 4 2.
No, I didn't.
Okay,
Yes, you
alright.
did, you did say 4 2.
Alright, that's the reason why you wanted to make sure that if I write on the board, then tell me, oh, Miss Morris, I said this instead. So,
That's why I said you're 100% sure that that answer that you put up there is right.
no.
I
Alright,
asked that.
no. You need to make sure that whenever I copy down that you ask me, that I was saying for the answer for the book is right. Don't try to change it just because you're upset that I misheard you or that you weren't clear
Oh, I
before.
wasn't,
So make
I was
sure.
mad at myself because I thought I got it wrong.
Okay, that's part of the reason why, well, you did, because you forgot your 50. So that's part of the reason why you want to make sure that whenever you're telling it, because you said you forgot your 50 whenever you're adding it to your 40. So, if I copy it down over what you said wrong, then just fix it and say, oh, Miss Morris, I meant this. But don't try to fix it halfway through because you're upset that you got the wrong answer. So you go, okay, so do you understand? Yes, ma'am? Okay, so your book points out that technically they started off with 25.0. They want it rounded it to 3 sig figs. So for the final answer, how would you round it to 2 3 sig figs? Quentin.
Is it 3?
Yep.
Okay, 56,000.
You say 56?
76,000.
There you go. Let's okay. Maybe it's the math, but I just want to make sure. And what was the last part? Just 76,000? 3 sig figs.
Oh, 76,600.
There you go. Do you put a decimal point? Alright, so if all of these are in joules, what should your answer be in?
Souls.
Joules. Alright, so that's the final answer. I think Jamie can see it? Yes, Jamie can. Alright, anyone have any questions about this? This is a very good practice problem.
Do we have to do this again?
Yep. Alright, application. You don't have any homework, so I'll let you get started practicing for this one. So, application number 2 on page 88. They break it down a lot smaller instead of doing it in one big massive step like this. They're just making sure how much heat is needed to accomplish each of the following. So, figure out, okay, what am I doing? Am I doing temperature change? Where I need this one, application number 2 on page 88. Alright, so saying how much heat is needed to accomplish each of the following. So you're saying, okay, am I using specific heat with temperature change, like for this one? Or am I going from one state to another? So it's combining both of them, but it's checking to see, okay, are you thinking it through? So that's what it's getting at for that set for number 2. So figure out, okay, what problem do I need to use for it?
How are you supposed to know how much heat is needed for melt 60.5 grams of ice at 0?
That sounds like you have a chart that you can use for that.
Okay, so you do use the chart.
You can use the chart.
Dude, we use the same formula we used there.
For which problem are you looking at?
Two. Hey.
Let me get over there.
I'm It looks like I'll-
Okay, I see now. So you're melting 60.5 grams of ice at 100 degrees Celsius. So if I'm just melting, do I use this equation?
0.0 Celsius.
Thank you. So for this one, if I'm just melting it, am I doing temperature change or am I just melting it going from one state to another?
isn't it just gonna be
You're
zero?
going one for another.
You're going from one, hang on, I can't go from two to one. You're going from
You're
one state to
going
another,
from ice to
so,
liquid, right?
what?
You're going solid to liquid, aren't you? melt.
Yes, you're going from a solid to liquid. So, what is the heat of fusion for water? You have to find it at the top of the table.
Like what, 4.81 or something?
Okay, that's specific heat.
Oh. Heat of fusion?
Heat of fusion.
What is it? What is the what?
What's the heat of fusion for water? It's at top of page, I think, 84 or 86? Yeah, 86. So, look for water in the chart, and then go across. Okay, heat of fusion. Don't get distracted by melting point. Where's heat of fusion?
You want to do the same thing?
Okay, that's the melting point in Kelvin. So go over one more.
I see it.
Alright, 234. So that's for 1 gram though. Are you doing, how many grams do you have in part A?
60.5.
Alright, so what do you do?
Multiply that by 334.
Yep, that'd be true. Alright, so does that
How
answer
did
your
you
question?
No, how did you do that again?
Okay, so, no, for this one, you're just melting it. So, if I'm going from a solid to a liquid, am I doing state changes or am I doing a temperature change?
So, wait, so melt 60.5 grams per zero. So you would just do 60.5 times that, right?
Yeah, no, the chart is at the top of page 86, but there's a lot of information, so don't be distracted. But yes, it is just 60.5 times 334. That's how much heat is required to just melt this amount of water. Alright, which is what, Ethan? Did you already figure it out? This is what we can all check together?
20,207.
Good job. So, 20,200.
Is the chart?
It's 86 or 87. Let me look at it real quick.
And B, you do the same thing.
87 is the top of the chart.
On B.
You know, it
you
says
do the same
enthalpies
thing.
of phase changes. So there's all of them, but they're giving it with your formula, your melting point, the heat of fusion, boiling point, and heat of vaporization. So we're sure to check to see, okay, what am I looking for in those 5 parts? Like for number B, it's vaporizing water at 50 grams of water at 100 degrees Celsius.
So on the next one, you're doing the same thing.
Yeah, well, it's heat of vaporization. It's what's the heat of vaporization for water? Yeah, find that chart.
2260.
Yep. So 2,260 times how many grams comes in? 50. So yeah, so it's just 50 times 2,260.
Did you already do this?
We practiced
I
before.
feel like
Yeah, I
we
did do this
practiced.
as an example one. So how much is it?
13, or 113.
There you go. And then this one, and what's your units for it?
Joules.
Yep.
Yeah, and C is 300,960 euros.
Good job. Yes, it is.
Wait, hold on, let me do it. So like on number B, what does 100 degrees Celsius have to do with anything?
It's just saying you're just evaporating it. So, like looking at this one, yeet. Alright, you're going from water to gas at 100 degrees Celsius. That's the boiling point of water. So it's saying, okay, we're taking 50 grams of water and we're evaporating it or vaporizing it. So, you're taking 50, multiplying it times 2,260. I forgot that was an actual problem we gave you.
So C is basically the same thing as B.
No. Okay, so it says, so that when you're heating up 90 grams of water from 18 degrees Celsius to 98 degrees Celsius, will you have a state change in that one?
So that means you have to use the other table?
Well, what equation would you use if you're gonna go
That
with,
one?
yep, this one. So, do you know what, for this one, it's water. Do you remember what specific heat of water is though?
4.18.
Yep, so, I mean, you can look it up, but yeah, it's 4.18. So, 4.18 times how much water do we have in letter C, Chris?
900.
Yep, 900 grams.
You know what temperature do you use?
Alright, you're going from 18 degrees Celsius to 98 degrees Celsius, so what's that temperature change? How do you figure it out?
98. So you do subtraction?
Mm-hmm. So, it's 98 minus 18, that'll tell you how much it went up by.
70?
You can go ahead.
80.
You can start working on, you can go ahead and start reading over, I don't think I have time to talk about, but we'll talk about tomorrow. So
The
page
answer-
88 to page 89, and then go ahead and do concept review number 1. So we'll see time for homework.
The answer is 300.
Like tomorrow?
1,900.
Yeah. So, if you wanna start doing the concept reviews, you can, so that'll get you
Number
one. If you wanna start with number one, you might get to number two, maybe, see how fast you work. Alright, so what was your question, Ethan? Sorry, I started with 3
The
bullets.
answer is 300,960 per seat.
Yep.
And then D is basically the same thing.
Alright, D is the idea of you're heating 20
same
grams of
formula.
ice at negative 35 degrees Celsius to 0 degrees Celsius,
So you're
so,
adding, basically, right?
what?
Aren't you adding the negative 350 to 0? Cause you're going up 35.
Yes, so it's positive 35 temperature change. Alright, Quentin, I wanna help you because you look lost. Alright, so, did you get the answer for letter C already? Alright, letter D, so how do I set it up?
The same as Steve was saying,
So, how many grams of ice do I have?
20,
Yeah, there you go. What's the specific heat of ice? Did you find it?
no.
If not, it's okay.
Wow, what you told us?
To read the next pages, I think it's 87 is where it is, and then work on the concept review, I think on page 88 or 89. I forget when it swaps over. But it's just the next concept review. That'll be tomorrow's homework.
How many questions, we're doing all 4?
Is it 2.06?
Yep. Alright, and then what is the heat change if I'm going from negative 35 to 0? 35. So just move them all together, what do you get?
9,442.
Yep, that's it. And then what's your unit, and then what's your units?
Cool.
Yep, that's it. Alright, really quick though, pause what you're doing. Anyone have any questions about how to do what we just did? Okay, so again, it's straightforward as long as you know what you're doing. So if you're trying to take shortcuts or do it quick, it won't work for you. Alright, so you can go ahead and close your textbooks right now, so that way we can review just like the last minute, because I'm about to be out of time now. Alright, close your textbooks, Ethan. Alright, so if I'm going from solid to a liquid, what do we call that? Like, what is that heat that's required to go from a solid to a liquid? Quentin? It doesn't say on that one.
No.
Alright, solid to a liquid. Alright, you remember?
Heat of vaporization?
Not heated, because you're going from a solid to a liquid.
Heat of,
Condensation.
Nope.
is it heat of,
No.
some weird, is it heat of something, right?
It is heat of something. It's not
Oh,
vaporization.
heat of-
Unit of, fusion.
Heat of fusion, so you're going from a solid to a liquid. What if you're going from a liquid to a gas? Now it's what?
Heat of, and condensation.
What did I get?
Heat of vaporization.
Heat of vaporization. What if I'm going from a gas to a liquid? Am I taking heat in or taking heat out? Taking heat out. Bye. Have a good day.